Every single time you use the internet, you're interacting with this huge, invisible bureaucracy. It's a system that's always working silently in the background, just making sure your browser finds its way. So today, we're going to pull back that curtain and take a look at the system, the Domain Name System, or as you probably know it, DNS.
Welcome to Recursive. Unlock the secrets of the internet and master computer networking. Let's dive in.
Think about it. It's something you do dozens, maybe hundreds of times a day. You type a name like google.com into your browser, you hit enter, and poof. A split second later, the page just appears. But what actually happens in that tiny little gap? It feels like magic for sure, but it's actually this brilliant high-speed chase happening across the entire internet. Well, to get online, your computer needs 4 key pieces of information. Now, you've probably heard of the first 3. Your IP address, which is like your digital street address, a subnet mask, and a gateway, which is your door to the wider internet. But that 4th pillar, the DNS server, that's the real unsung hero here. Without it, the internet would technically still work, but it would be completely unusable for us humans. We'd have to memorize long strings of numbers for every single website we wanted to visit. No way. Now, DNS isn't just one single server doing all the work. Oh no, it's a whole team, an entire office full of specialists, and each one has a very, very specific job. So let's meet the key players in this digital bureaucracy. First up, we've got the caching name server. Think of this as the office assistant with a really great short-term memory. If someone in the office just asked for a specific address, this server remembers it for a little while, so it doesn't have to go through the whole process of looking it up all over again. It is all about speed and efficiency. Next is the Recursive Name Server. Now, this is our main character. This is the workhorse investigator of the DNS world. It's usually operated by your internet service provider, and when that caching server, the one with the good memory, doesn't have the answer, this is the one that says, okay, I'll go find it, and it kicks off the entire investigation. At the very top of the hierarchy, we have the root name server. This is the CEO, the top boss. It has no idea where weather.com is, and it doesn't need to. Its only job is to know who manages the different departments, like the server for all the .com websites, and to point our investigator in the right direction. So the root server points us to the department managers, the TLD, or top-level domain name servers. There's a manager for the entire .com department, there's another one for .org, another for .gov, you get the picture. They manage these huge lists of websites, but they still don't have the final answer themselves. Their job is to just narrow the search down even more. And finally, we arrive at the Authoritative Name Server. This is the source of truth. It's the server that holds the definitive record, the actual IP address for a specific website. When our investigator finally reaches this server, the search is officially over. Okay, so now that we've met the whole team, let's see how they work together. Most of the time, the internet uses this really clever shortcut to make things incredibly fast. So let's look at the simplest scenario first. Okay, imagine you and a friend are on the same Wi-Fi network. Your friend goes to facebook.com. The recursive server at your ISP does the full investigation we just talked about. It asks the root, then the TLD, and then the authoritative server to find the IP address. Then, and this is the critical part, it saves that answer in its cache. So a few minutes later, you type in facebook.com, the server doesn't have to do that whole search again. It just goes, I remember this one, and gives you the IP instantly. Your page loads faster, all because of your friend's search. But wait, what if a website changes its IP address? We can't have servers holding on to old, wrong information forever, right? That's where something called TTL, or time to live, comes in. It's basically an expiration date, a timer attached to every single cached record. It tells the server, hey, hold on to this answer for, say, 300 seconds, and after that, just throw it away and ask for a fresh copy. This makes sure all the information stays up to date and accurate. Okay, so caching is great, but what happens when the information isn't in the cache? This is where our investigator, the recursive server, has to do some actual work. So let's follow the complete chain of command for an address that nobody's looked for recently. The journey is always the same 3 steps, a really clear and logical hierarchy. A recursive server needs to find weather.com. It starts at the very top by asking the root server. Then it gets sent down to the TLD server, and finally it gets the answer from the authoritative server. So the first conversation goes something like this. The investigator asks the root server for weather.com, and the root server, our top boss, doesn't know the specifics. It just knows which department handles .com addresses. So it basically says, I don't know where weather.com is, but I know who handles.com. Go ask the TLD server. And sends our investigator on its way. And here is an absolutely mind-blowing fact. For the entire global internet, there are only 13 of these root server authorities. Just 13. So how can so few servers possibly handle every single initial DNS request from billions of people all over the world? Well, the answer is a brilliant piece of network engineering called Anycast. See, while there are only 13 authorities, their addresses are mirrored on hundreds and hundreds of physical servers all over the globe. So when you send a request, Anycast technology automatically routes you to the server that is physically closest to you. This makes the response incredibly fast, and it spreads the workload out so no one server gets overwhelmed. Pretty smart, right? Okay, back to our investigation. Our server now asks the .com TLD server, the department manager. The TLD server is one step closer. It doesn't know the final IP address either, but it has a record of the specific server that is the authority for the weather domain. So it provides that final address and says, I don't know the specific IP, but I know the authoritative server for weather. Go ask them. And this is the final stop. The investigator asks the authoritative server, and it gets a definitive answer. Yes, I'm the one you're looking for. I am the weather channel. The IP is 184.29.131.121. Boom, the search is complete. The recursive server can now send that IP back to your browser, and of course it caches the answer for the next time. So it might seem like a really complex bureaucratic process, a lot of back and forth, but there's a real elegance to this design. It's what has allowed the internet to scale up from a tiny academic project to the global network we all rely on every single day. And this is really the genius of the system. The strict hierarchy means there's a clear, reliable path to find any answer, which prevents total chaos. The combination of caching for common requests and Anycast for new ones makes the whole system blazingly fast. And that rigid chain of command makes it much, much harder for bad actors to jump in and send you to some malicious website. It's a system built from the ground up for scale, speed, and security. This silent, invisible system is a fundamental pillar of our digital lives. It works so well that we almost never even have to think about it. But it does leave us with a final question. What would happen if this chain of command, this invisible bureaucracy, were to just break? The internet as we know it would simply cease to function. Something to think about the next time you hit enter.